Bismillahirrahmanirrahim. Electromagnetic field theory, and today our topic is about Savart law. But before about Savart law, we have to solve few numericals related to the purest topic, that is the electric potential at a point. So let's start with drill 4.8. We are given with V is equal to 60 sine theta over r square, and the given point is P. R is equal to 3 meter, theta is equal to 60 degree, and phi is equal to 25 degrees. So it means the point of observation is in spherical coordinate system. So the first point is we have to find VE and EP, the second point. So solution, VP, A part is very simple. Just we have to put the point R is equal to 3 meter and theta is 60 degree in this equation, and there is no phi involved in this equation, so this will be useless. So 60 sine 60 degree over 3 square, so we will get Vp is equal to 5.77 volts. Now we have to find the electric field intensity at that particular point. So using this expression, E is equal to minus divergence dot V. So divergence of V is equal to E minus E. So putting the values of V from the given equation, 60 sine theta over r square. So for the AR term, the theta will be considered as constant, and the partial derivative will only be applied to the r square. And similarly, in the theta portion, the differential will the partial derivative will only be applied to the sine theta, and r square will be considered as a constant for this differentiation. Okay, and there is no phi term involved, so this will be automatically zero. So applying the partial derivative, we will get 120 sine theta over r cube. Okay, this is because of the square. So this due to square 2 will we will get 2 at the coefficient, so this 2 will be multiplied with 60 to get 120, and minus 2 minus 1, so this will be equal to r raised to the power minus 3, which is equal to 1 over r cube. Okay, and this r will multiply with this r square to get the r cube, while the derivative will only be applicable to the sine theta to get cos theta. Okay, so very simple. Okay, now we have to find the rho v. Rho v actually, uh, the divergence of the d is equal to the volume charge density. We have already proved this Maxwell equation in the previous lectures. So using this expression, we have to find the volume charge density. Okay, so again, we have uh, the v value. Okay, uh, so now the e is given. Okay, from here we will mm, we will use the e, but e is equal to d is equal to epsilon naught e. So from that we have to put the e values, and later on we have to multiply the e epsilon naught to get the proper expression of d. Okay, so for the time being, uh, I apply the partial derivative to this expression, 120 sine theta or r cube. So we will get 120 sine theta over r square and 1 over r square. Okay, so and from this expression we will get 30 over r square sine theta, partial derivative of with respect to the theta minus sine 2 theta. Okay, so we will get after putting the values of r is equal to 3 and theta is equal to 60 degree, we will get the divergence of d is equal to minus 7.57 picocoulomb per meter cube. Okay, now the second example is related to the dipole. Okay, as we have already explained this in the previous lecture. So q, the plus q is equal to 3 microcoulomb, which is placed at z-axis at a distance of 1 millimeter. And now minus q, which is having a same coulombic value of minus 3 microcoulomb, and placed at a distance of minus 1 millimeter on the z-axis. Look, x is equal to 0, y is equal to 0, only z value is given, so it means the charges are placed on the z line, z axis. Okay, we have to find the p is the dipole moment, and E, electric field intensity. Okay, okay, and we have to find the E at some different point, 1 comma 2 comma 1.5. Okay, so the dipole moment is located along the z-axis. So this is the figure, plus q minus q. Okay, along the z-axis, 0 0 1 and 0 0 minus 1. Okay, and the q is given 3 microcoulomb. So for the solution of the first part is p is equal to d q d. Okay, q is 3, d is given, that is 2, because from here we have 1 millimeter, and from there 1 millimeter, 1 plus 1, 2 millimeter. So 2 into 10 is power minus 3 meter. Okay, so we will get 6 nano coulomb meter in the direction of az. Okay, now b part, E is equal to q d 2 cos theta AR plus sin theta A theta divided by 4 pi epsilon naught R cube. We have already derived this expression in the theory. So just apply that expression and putting the values of Q, which is 3 micro, D is 2 milli, and theta is given, that is 40 degree, R is 2, phi is 80 degree, but there is no phi term, so this will be useless. So after putting the values, calculating it, and we will get 10.33 AR plus 4.33 theta volt per meter. Now the C. Okay, so first of all we have to find the R for this point, uh, which is 1 square plus 2 square plus 1.5 whole square whole square root, which is equal to 2.69. And now the theta, because theta will be used, so theta is equal to cos inverse z over r. Z is 1.5, r is 2.69. So cos inverse of this will be equal to 56.1 degree. Okay, so now we have the theta value and the r value for this given point. So putting these values in the expression, we will get E is equal to 3.1 AR plus 2.29 A theta volt per meter. So the part B and C are almost similar, but we have the different points of a different coordinate system. Okay, the point for the B is given in spherical coordinate system, while that of the C part is given in rectangular coordinate system. Okay, so now switch towards the Savart law. But before Savart law, I will let you know that we have finished the electrostatics portion, and now we are switching to the magnetostatics portion. That is the second part of this course. Okay, electromagnetic field. Okay, so we have covered the electro theory, and now we are switching to towards the magnetic field theory. Okay, so as you know that the current carrying conductor. Okay, a magnetic field surrounds around the current carrying conductor, and that the direction of the magnetic field can be found by the right hand thumb rule. So if this is the direction of the current, so it will indicate the thumb direction, while the fingers will indicate towards the direction of the magnetic field. Okay, so According to this law, at any point P, magnitude of the magnetic field intensity produced by a differential element is proportional to the product of the current 1, the magnitude of the differential length 2, and the sine of the angle lying between the filament and the line conducting the filament to the point of observation P. Okay, that is 3. Where field is desired, okay, the magnitude of the magnetic field intensity is inversely proportional. These three were directly proportional, and now the only inversely proportional term is the square of the distance from the differential element to the point of observation P. Okay, now explanation. Consider a current carrying conductor, and the current is moving in the conductor in upward direction, as you can see from this figure. And this is the differential length of the this conductor filament. Okay, and from that differential length, mm, r is the position vector from this current carrying conductor to the point of observation, while the current carrying conductor is at a distance of r1 and point of observation at distance of r2 from the origin respectively. Okay, so we have to apply the right hand rule to find out the proper direction of the magnetic field. Okay, B represents the magnetic flux density and H represents the the magnetic field intensity. Now we consider a small segment of the conductor represented by dl. The direction of the vector quantity is in the direction of the current. Then, according to the Bivot-Savart law, the differential flux of the point of observation is proportional to dB is directly proportional to I, as I have clear. dB is directly proportional to dl. dB is directly proportional to sine theta and inversely proportional to the r square, where theta is the angle between the distance vector and the current carrying conductor. Okay, so accumulating these variables to get dB directly proportional to I dl sine theta over r square, where k is the proportionality constant, and that is equal to a mu naught over 4 pi. Okay, so replacing this value with the k, so we'll get this. Now consider a unit vector ar along the distance vector r. Okay, if we have ar in the direction of r, so the cross product of dl and ar will be equal to the magnitude of dl is dl, and the magnitude of unit vector is 1. So, and the sine theta an, this is because of the cross product. Okay, so replacing the dl sine theta with this cross product, so we will get I dl cross AR over R square, and this is the expression for the dB. Now for the H, we have to divide this whole expression by the mu naught. So mu naught of this expression will be cancelled out with this. So we will get dH is equal to 1 over 4 pi. Okay, the mu naught will be cancelled out, and I dl AR cross AR over R square. So for the unit vector, as we know that AR is equal to vector over absolute of that vector. So putting these values, we will get mu naught over 4 pi I dl cross R over R cube. This is the expression for the dB, and for the dH, this mu naught will be cancelled out with this. So we'll get 1 over 4 pi I dl cross AR over R square. Okay, and that will be equal to 1 over 4 pi, replacing these values over here, so we will get I dl into r over r cube. In order to find out the total flux density, these were the flux density and the magnetic flux intensity for the small segment. Okay, now for the complete length, we have to apply the integration for this differential length. So mu naught over 4 pi integration I dl into cross AR over R square And if you replace this AR by this expression, so we will get IDL cross R over R cube. Okay, so and if you want to find the H value for the complete filament, so this is also simple. H is equal to 1 over 4 pi integration I dl cross AR over R square, and that will be equal to, okay, I will write over here H is equal to mu, so no, there will be no mu naught. Okay, so 1 over 4 pi. Okay, and I integration I dl cross AR or R square. And if you want to replace this AR with this in term of R, so you will get H will be equal to 1 over 4 pi integration, and this will be integration with respect to dl. Okay, limits of the length will be put for this integration. I dl cross R over R cube. So that will be the magnetic field intensity for the complete filament. So we will discuss the numericals of Bauer-Savart law in the next lecture. So that was all about the first session of the lecture, in which we have discussed the numericals of the electric potential and the dipole moment, and then the statement of the Bauer and expression for the Bauer-Savart law in term of the magnetic flux density and magnetic field intensity. Okay, so remember B and H. Okay, and these two are in the relation with this mu. Okay, so we will discuss the numericals in the next lecture. So thank you. Okay, the steady magnetic field. Okay, so that was about this Bivot Savart law. Thank you.